First we used the 7402 IC. As you can see, if we push button 1 we get positive output, and also if we push button 2 we get positive output, but if both buttons are pushed at the same time we get negative output. Then we put our results in a truth table. Then it could be seen that the gate we had was an AND gate. The NAND gate operates as an AND gate followed by a NOT gate. The output from an AND gate is false if both inputs are true, but the output is true if either of the inputs are true or if both inputs are false. Next we used the 7408 IC. Now we had to push both buttons to get a positive output. In the truth table it can be seen that the gate is an AND gate. For an AND gate, the output is true when both inputs are true, otherwise the output is false. Next we used the 7432 IC. We always got positive output except when both inputs were negative. From the truth table we found out that we had an OR gate. The OR gate behaves like the name says. The output is true if either or both of the inputs are true, but if both inputs are false, the output is also false. For the 7486 IC, we saw that we got positive output when we pushed either of the buttons. The XOR gate, or the exclusive OR gate, acts in the same way as the logical OR. The output is true if either but not both of the inputs are true. The output is false if both inputs are false or if both inputs are true. The 7404 IC only has one input. When we push the button and give positive input, we got negative output. From the truth table, it can be seen that we have a logical inverter, also called a NOT gate. The inverter reverses the logic state. The last IC was number 7402. We only got positive output when both inputs were false. From the table, we can see that we have an OR gate. An OR gate is a combination OR gate followed by an inverter. Its output is true if both inputs are false, otherwise the output is false. In part 3, we used the IC that includes NOR gates, which was the 7402 IC. We connected the NOR gate according to the schematics we got. We used the push buttons to find out the type of the gate being mimicked by writing down the output results in a truth table. Then we compared the truth table to our previous tables and found out the name of the resulting gate. The first gate being mimicked was a NOT gate according to the truth table. The next gate being mimicked was an OR gate. And the last one was an AND gate. At last we used the IC that includes NAND gates, the 7400 IC. We connected the NAND gate and used the same method as before to find out the gates that were being mimicked. The first gate that was being mimicked was a NOT gate. The next gate was an AND gate. And the last one was an OR gate. In the first part, we built a half adder. Half adders take in two binary digits and return sum and carry. The setup was similar to the setup in the first exercise. We tried all push buttons and put the results in a truth table. When both inputs are negative, we are summing 0 to 0, which of course gives 0, so we have negative outputs in both lights. When either of the inputs are true, we are summing 1 to 0, which gives 1, so we get a positive output in the sum light. We get negative output in the carry light because we only need one digit, so the carry light doesn't need to carry any digit. The 1 goes to the first digit, which is the sum light. When two positive inputs are summed, we need to carry 1 plus 1 to a second digit. That is what the carry light is supposed to signify. Next, we built a half subtractor. The half subtractor takes in two binary digits and returns difference and borrow. We built the circuit. Same parts were used as for the half adder, but we added a NOT IC. We tried all push buttons and put the results in a truth table. When both inputs are negative, we get negative outputs in both lights because the difference is 0. When button 2 was pushed, and therefore gave one positive input, we get true outputs in both difference and borrow lights. The reason for that is when we subtract 1 from 0, we get -1, but -1 is not a binary number, so we have to borrow one output. So the result is 1 for difference light and 1 for borrow light. When button 1 was pushed, we are subtracting 0 from 1, which gives 1, so we only get positive output in the difference light. At last, when both buttons were pushed, we subtract 1 from 1, which gives 0, so we get negative outputs in both difference and borrow lights. In part 2, we built a simple memory unit, the SR latch. The SR latch is the most basic type of a flip-flop. We connected the push buttons to the set and reset inputs on the IC. Then we connected the outputs Q and not Q. The Q and not Q outputs are supposed to be in opposite states. When neither of the buttons were pushed, the Q light got lit. It is completely random which light got lit in the beginning when we turned on the LOS board. When we reset a flip-flop, the not Q light goes high. When we set a flip-flop, the Q light goes high. When both buttons are pushed, we are setting and resetting at the same time, which can't give positive output, so both Q and not Q were negative. In part 3, we used up the multiplexer and chose our input to match a certain output. First, we connected the first 8 outputs to LEDs and pushed buttons A0 to A2 to get the correct output. We didn't have to push any button to light up LED number 1. To light up LED number 2, we had to push A0. We see that the buttons act as digits in a binary code for the binary value of each LED activated. We didn't have to use button number 4 this time because the binary code for binary values 1 to 7 only have 3 digits. Next, we changed which outputs on the demultiplexer were connected to LEDs and now pushed buttons A0 to A3 to get the correct output. This time we needed button A3 because we were doing the binary code for binary values 8 to 15 and they have 4 digits. JK flip-flops are a memory unit similar to the SR latch from practical exercise 2. This table shows basic schematic outlines and useful information regarding their inputs, outputs, and function. In hold state, both inputs are negative and the output shows no change. In reset circuit, we have J as a negative input and K as positive input. The output changes from Q to Q next. In set circuit, we have J as a positive input and K as a negative input. The output changes from Q next to Q. In toggle circuit, both inputs are positive and the output changes from Q to Q next and then switches back again, so basically there's no change. In this exercise, we built a circuit using a clock and counter circuit leading to a 7-segment display. The 7-segment display is driven by a 555 timer and a 4-bit counter. The 555 timer IC generates clock pulse, which generates the count in the 4-bit counter, which is then displayed on the 7-segment display. IC pin connection were unknown, so we had to figure out which connection worked. By connecting the circuit in different ways, we found out that the clock is in pin 12, Q in pin 1, and Q next in pin 4. We had 6 different capacitors with various capacitance. By switching the capacitors in the circuit, we saw that the higher the capacitance is, it takes the capacitor longer time to charge, and therefore it takes longer time to change the digit on the 7-segment display. While the capacitor is charging, the display shows a digit. When the capacitor is fully charged, it starts to discharge. That happens much faster than the charging. When the capacitor is completely discharged, the 7-segment display shows nothing. When it starts to charge again, the digits change.
By connecting the push button to pin 2, the circuit had another clock which we were able to stimulate, and therefore the display received 2 pulses. If we switch the push button connection from pin 2 to pin 15, the circuit still has 2 clocks, but now the button works as a reset button for the display. In the last part, we connected the circuit to a serial connection of D flip-flops to create a shift register. We modified the 555 timer circuit, then we added 2 D flip-flops and 4 LEDs. When the button was pushed, it sent current to the first flip-flop, so the first LED was lit. Then this flip-flop sent current to the next flip-flop, so the second LED got lit, and so on to the fourth and last flip-flop. In part 1, in exercise 4, we put together a photoplethysmographer using an infrared light and several classic devices. A photoplethysmographer is not only clinically relevant, but also very inexpensive. This is done through an infrared light emitter and an infrared detector that picks up the light that scatters off the oxygenated hemoglobin in nearby blood vessels. The circuit will filter this infrared signal and employs the AC component peak to light a LED, which will therein serve as an indicator for the heartbeat. By setting up a passive high-pass filter and an active low-pass filter, we can filter and amplify the V-sensor output. By filtering, we are determining a certain row of frequency. For the passive high-pass filter, we chose a cutoff frequency of 0.7 Hz, and for the active low-pass filter, we chose a cutoff frequency of 2.34 Hz. Here we can see how we calculated which resistors and capacitors we needed for the circuit. Here we can see that when a finger is put on the sensor, the LED lights up in the same rhythm as the heartbeat. In part 2 of the exercise, we added the 555 timer circuit that we built in exercise 3 with our photoplethysmographer. With this, we could record heartbeats per minute, both in rest and after some exercise. We tested one person in our group. Her resting heartbeat was 64 beats per minute, and after some exercise, her pulse went up to 80 beats per minute. That shows us that the device is good enough to measure the increased heartbeat.
In the last exercise, we constructed an electromyography circuit that utilized minute muscular depolarization in our muscle to drive an LED. This unit is the INA 118 instrumentation amplifier. We connected VN plus and VN minus to electrodes which we placed on our bicep, 2 centimeters apart from each other. We connected ref, which is the reference pin, to a voltage divider. We could choose any resistance for R1 and R2. We chose 100 ohms. Then we connected V out to an electrode which we placed on our elbow so the circuit and the body were both grounded. We found the value of Rg, which is the gain resistor, by using this formula. We put the total gain of the amplifier as 10. Then we continued from V0. We assembled a second-order bandpass. We did that by combining a second-order high-pass and low-pass filter with our MCRP 6004. We were given a formula for the second-order low and high-pass cutoff frequency, so from that equation we could find the resistances and capacitances for both high and low-pass filter. The ideal range for EMG is 10 to 500 Hz. For the high-pass filter we needed low frequency, but for the low-pass filter we needed high frequency. It took some time to figure out which frequency we should use for our device, but in the end we found out that 200 Hz worked for the high-pass filter, 8 kilo-ohm and 100 nanofarad. For the low-pass filter we used 6.4 ohm, 62 microfarad, so the frequency was 400 Hz. The resistors and capacitors were equal within both filters because we didn't want to amplify any noise around us. We finished our circuit with a non-inverting amplification circuit. To find the resistances, we used this formula, where we put the gain as 500. It took some time finding the right resistance values, but in the end we used 6.2 kilo ohms for RF, so then we got the value 13 ohm for the RG. At last we connected the V out to our LED. As you can see, our device worked for the bicep. Every time the muscle was flexed, the depolarization of the muscle sent current to our device, which turned on the LED. We also tried measuring the function in the calf. Our device worked as good for that muscle.